Welcome to lecture 30. So this is the last lecture for the ring theory part, and in this lecture today we will discuss various examples and solve some problems on the topics that I have covered so far in the ring theory. So let's start. So last time we have defined what is the nil radical and what is the Jacobson radical, and we have seen some characterization of the nil radical and Jacobson radical in a ring. Today we will give you some examples of nil radical and Jacobson radical. So last time we have defined what is a local ring. So if you remember, so a local ring is nothing but a ring with a unique maximal ideal. So in that case, what will be the Jacobson radical? So if R is a local ring, then in that case the Jacobson radical of R is nothing but the unique maximal ideal. Unique maximal ideal of the ring R. So in that case we have a easy description of the Jacobson radical, which is nothing but the unique maximal ideal. Now if you are in a domain, then what will be the nil radical in that case? So if R is a domain, then I know that domain means 0 is a prime ideal, and when I consider the intersection of all prime ideals, then it will be eventually 0, as 0 is a prime ideal. So in if R is an integral domain, in that case our nil radical is 0 ideal. So if R is a domain, then nil radical of R is nothing but the 0 ideal. So if it can happen that sometimes the nil radical may be equal to Jacobson radical, but sometimes it may not be equal to the Jacobson radical. So for example, if you are in the ring of integers, then we will see that in this case the nil radical and the Jacobson radical are same. So example, in Z, the nil radical and the Jacobson radical is same, which is nothing but the 0 ideal, because Z is an integral domain, and in integral domain we know that intersection this nil radical is 0 and this is only the 0 ideal. So here nil radical is 0, that is obvious. Only thing we need to prove that Jacobson radical will also be 0. That means the intersection of all prime ideal should also be equal to 0. Now you can see it in the following way. So we will use the characterization that just for your recall, that we say an element x is in the Jacobson radical if and only if 1 minus xy is a unit in R for all y in R. So this is the characterization that we have seen last time, and we will use this characterization to show that the Jacobson radical is nothing but the 0 ideal in this case. So let A, so let A be an element in the Jacobson radical of R, then 1 minus 3A is a unit in Z, because using this characterization 1 minus xy for all y should be unit. So I am particularly choosing the element 3, then 1 minus 3A should be a unit. What are the units in Z? It is 1 or minus 1. So if 1 minus 3A is equal to 1, this implies that A has to be equal to 0. That means there is no non-zero element in that case. And if 1 minus 3A is equal to minus 1, that is the other unit in Z, then in that case I am getting my A to be equal to 2 by 3, which is not possible, because A cannot be 2 by 3 because A should be an integer. So, which is not possible. Hence, in this case, the Jacobson radical of Z, just here I should say it is Z. So, Jacobson radical is nothing but the 0 ideal. So, this is an example where we have seen that the nil radical and the Jacobson radical are equal. Now, I will solve one problem here. So, I would like to find the nil radical, find the nil radical of Z quotient 12Z. So, the ring is the quotient ring Z quotient 12Z, and we would like to find the nil radical of this ring. So, of course, this is not an integral domain. So, we cannot say that in this case nil radical will be 0. So, let us see how to find the nil radical for this ring. So, nil radical is nothing but the set of all nilpotent elements. So, if an element is nilpotent in this ring, what does that mean? So, an element A plus 12Z is nilpotent if and only if some power of this element, so A plus 12Z, some power should be equal to 0 for some k positive. What does this mean? This means that A to the power k should belongs to the ideal 12Z. This implies that 12 should divide A to the power k. Now, if 12 divides A to the power k, that means all its prime factor also divide. So, this implies that 2 divides A to the power k and 3 also divide A to the power k, which is equivalently saying that 6 divides A to the power k. Or more precisely, I can say that 12 divides A to the power k, that means 2 divides A to the power k, which is in some sense saying that 2 divides A and 3 divides A, and therefore, their product 6 divides A. So, now I will, so this says that if A is nilpotent, then 6 should divide A. Now, I will prove that any multiple of 6 is in fact a nilpotent element. So, for that, conversely, if 6 divides A, I would like to prove that it should be a nilpotent element. In that case, you can observe that if 6 divides A, then 6 square, that is 36, should divide A square. So, this implies that the image of A square in 12Z is equal to 0 in the quotient, because A square is divisible by 36 and 36 is a multiple of 12. So, therefore, A square is in the ideal 12Z. Therefore, A square is 0 in this one. This says that A plus 12Z is a nilpotent element in Z quotient 12Z. So, which proves that when we will have a nilpotent element, so therefore, A plus 12Z is nilpotent if and only if 6 divides A. So, therefore, the nil radical of Z quotient 12Z is nothing but the ideal 6Z quotient 12Z. So, this identifies the nil radical of this quotient ring Z quotient 12Z, and you can generalize this idea for any arbitrary n, and you can write down what will be the nil radical for Z quotient nz from here. Now, as we have so far defined the notion of nil radical, let us define which is known as the radical ideal. So, what is radical ideal? Let I, we are basically generalizing the notion of nilpotent elements to any arbitrary ideal and defining the radical ideal. So, let I be an ideal of a ring R, then radical of I is defined as, so usually the notation to denote the radical of I is this, which is defined as the collection of all the elements in the ring R such that some power of x is in I. So, you can check similarly as we have shown that the set of nilpotent element forms an ideal, you can check that this radical of an ideal is also an ideal. So, you can check that this is an ideal of R, and in fact instead of I, if I consider 0, then radical of 0 is nothing but the set of all nilpotent elements, which is nothing but the nil radical of R. So, using this radical concept of radical ideal, we can say that this radical of 0 is the nil radical of R. So, radical ideal of the 0 ideal is nothing but the nil radical of the ring, and also it is clear that I will always be sitting inside the radical of I. Okay. So, this is how the radical of an ideal is defined, and the radical of the 0 ideal is the nil radical of the ring. And using the same proof that we have observed for characterizing the nil radical, where we have seen the nil radical can be written as the intersection of all prime ideals, we can now give a characterization of the radical of an ideal. So, let me write it down. So, it says that the radical of an ideal is nothing but the intersection of all the prime ideals P such that it contains the ideal I. So, here P is prime and P contains I. So, here you can see that the proof is exactly similar for the where we have proved that the nil radical is the intersection of all the prime ideals. This is exactly the same proof. So, if I write it down, then we have to consider the ring R quotient I. So, in R quotient I, if you observe, the 0 ideal is nothing but the ideal I, then if I consider the radical of I, then radical of I is nothing but the nil radical of the quotient ring. That is the nil radical of the quotient ring R quotient I is the radical of I, and we have seen the nil radical is nothing but the intersection of all the prime ideals. So, this is the intersection of all the prime ideals P such that P contains I and P is a prime ideal. So, this gives you the characterization of this radical of an ideal in a ring R. So, with this, this notion of radical, nil radical and Jacobson radical I have finished. Now, I will be solving some problems for you so that your concepts will be much more clear. So, first question. So, the first problem is that is there an integral domain containing exactly 10 elements? So, the question is, does there exist an integral domain which contains exactly 10 elements? So, we will show that it is not, there does not exist. Why? If you recall from the theory that I have covered so far, that a finite integral domain is always a field, that I have proved earlier. So, every finite integral domain is a field. And what is the cardinality of a field? And the cardinality of a field is p to the power n for some n and for some n positive and prime integer p. But 10 is not of the form p to the power n for any n, because 10 is just product of 2 primes 5 into 2. Therefore, there does not exist any integral domain with 10 elements. Hence, since 10 can't be written as p to the power n for any p and any n, therefore, there doesn't exist any integral domain with 10 elements. So, this is how you can argue that it is not possible that you will have an integral domain with 10 elements. Now, the next problem. That I will be proving. So, the question is the quotient ring R Z quotient 5Z X quotienting by the polynomial x square plus x plus 2. So, I am considering the polynomial ring over this field Z quotient 5Z and considering the polynomial x square plus x plus 2 and consider the ideal generated by this polynomial and considering this quotient ring, then the question is this quotient ring an integral domain? So, and more specifically, is it a field or not? So, is this a field? That is the first question, and if yes, then every non-zero element will have a multiplicative inverse, and then in that case the question is, in that case, if it is answer is yes, then find the inverse of the element 2x plus 3 plus x square plus x plus 2. So, the multiplicative inverse of this element in this quotient ring. So, let us see how to proceed this. So, in order to show that this is a field, this quotient ring, I need to investigate whether this ideal is a maximal ideal or not. And we know that this polynomial ring over a field is a PID, and in a PID every maximal ideal is prime ideal, and in polynomial ring over a field, every prime ideal is generated by an irreducible element. So, it is enough to check whether this is an irreducible polynomial or not. So, want to check whether the polynomial f(x) equal to x square plus x plus 2 is irreducible over this polynomial ring. You can see that if it is reducible, then it can be factored as product of two linear polynomials. So, that will be possible if it has any root in this z quotient 5 set, and you can observe that f of 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, none of them is 0. So, you can check that f of 0 is not 0, f of 1 is non-zero, f of 2 is also non-zero, f of 3 is also non-zero, and f of 4 is also non-zero. So, therefore, none of this, so maybe I should just write down 0 bar, 1 bar, 2 bar, 3 bar, 4 bar to denote the residue classes in z quotient 5 set. So, none of them is a 0, therefore, this polynomial thus f(x) is irreducible over z quotient 5 set x over this polynomial ring. Hence, the ideal generated by this is a prime ideal. And since this is a polynomial ring over a field, so therefore, this is a PID. Since this is a PID, and in a PID, every prime ideal is maximal Hence, the ideal generated by this polynomial f(x) is a maximal ideal in the polynomial ring z quotient 5 zx, and hence this quotient z quotient 5 zx by the ideal generated by f(x). This is a maximal ideal, therefore, this quotient has to be a field. Hence, this is a field. So, if you want to check whether some quotient ring is a field or not, then it is enough to check whether this polynomial is a irreducible polynomial or not. In fact, of course, this is a field means this is also an integral domain. Now, we have proved that this is a field. Next thing, we would like to find out the multiplicative inverse of 2x plus 3 in this ring. So, in order to do that, any element in this quotient ring will be of this form. Note that any element of R will be of the form a bar x plus b bar, where a bar, b bar are, this is the image in where the bar denotes the So, here you can note that any element of R will be of the form a x bar plus b bar, where bar denotes the image in R. Why? Because in this quotient ring in R, we are having the 0 element is nothing but x square plus in this quotient ring fx bar is equal to 0 bar. That means I am having that x square plus x plus 2, that means x square plus x plus 2 bar is equal to 0 bar. So, from here I can write down my x square bar as minus x bar minus 2 bar. So, therefore, using this relation that all the higher powers of x square onwards can be written in the linear form, I can see that any element in this quotient ring will be a linear polynomial of this form, where the coefficients are coming from z quotient 5 z. Now, if I use this relation, then order to find in try to find the multiplicative inverse, then what we will have is the following. So, a bar x bar plus b bar into the multiplicative inverse of 2 bar x bar plus 3 bar. So, this should be equal to 1 bar. This condition should be satisfied. So, I need to find out the coefficient a bar and b bar appropriately, so that when I multiply I should get 1 bar in the quotient. So, now let us expand this, and if you expand, then you will be getting 2 bar a bar x bar square plus 3 bar a bar plus 2 bar b bar into x bar plus 3 bar into b bar equal to 1 bar. Now, I will be using that relation that x square bar is equal to minus x bar minus 2, and I will substitute this relation here in x bar square, and if I do that, then I will get that 2 bar a bar into minus x bar minus 2 bar plus 3 bar a bar plus 2 bar b bar to x bar plus 3 bar b bar equal to 1 bar. This if I further expand and rewrite, then I will be getting something like this is will be a bar plus 2 bar b bar x plus 3 bar b bar minus 4 bar a bar equal to 1. So, from here you can see that if I compare the coefficients of this polynomial on both sides, then I will be getting that the coefficient of x should be equal to 0. That means this should be equal to 0, and I must have 3 bar b bar minus 4 bar a bar is equal to 1 bar. So, from these two equations, so let us number this equation as this as equation number 1 and this as equation number 2, then 2 plus 4 bar into 1 bar we get nothing but. So, this second equation is there, and the first equation we are multiplying by 4 and adding. So, the first equation if I multiply by 4, then this 4 bar a bar will get cancelled, and I will be left with the following, that b bar should be equal to 1 bar. So, I have got that my b bar is equal to 1 bar. Now, if I substitute the value of b bar here, then this implies that a bar should be equal to minus 2 bar, and 2 bar is nothing but 3 bar. Hence, the multiplicative inverse of the polynomial 2 bar x bar plus 3 bar is, so a bar is 3 bar x bar plus b bar is 1 bar in the quotient ring. So, if I write down, so this is same thing as saying that 3x plus 1 plus fx in R. So, this will be your multiplicative inverse of this 2x plus 3 bar in this quotient ring R. Now, so this gives you how to shows how to find the multiplicative inverse in the quotient ring of an element when it is a field. So, now let us see some more problems. So, next is exercise 3. So, the question is the ideal generated by 5 is a maximal ideal, is a maximal ideal in Zi. You remember that Zi is nothing but the ring of Gaussian integers. So, we will be using some of the theory that we have already developed, and so this 5 is a prime integer, and we would like to check whether this prime integer is a Gaussian prime or not. So, if for that we have already characterized what are the prime elements in Zi. So, and we have seen that here you can see that this 5 is congruent to 1 mod 4. So, if 5 is congruent to 1 mod 4, in that means that 5 is not an irreducible element. This implies that 5 is not irreducible. In fact, you can see that 5 can be written as 2 plus iota into 2 minus iota. And so, this is can be written as product of two other elements, therefore, 5 is not irreducible. Hence, the ideal generated by 5 is not a prime ideal, because Zi is a PID, and in a PID every irreducible element is prime element, and so therefore, this is not a prime ideal. And moreover, Zi is a sense Zi is a PID. So, every non-zero prime ideal is maximal, and hence the ideal generated by 5 is a maximal ideal. In Zi. On the other hand, if I consider the ideal, say if you consider the ideal, there is some mistake. This is not a prime ideal, and hence this is every prime ideal is maximal, and therefore, this is there is some mistake I have done here. I am sorry. Here 5 is not a prime ideal, and a maximal ideal has to be a prime ideal first of all. Therefore, this is not a maximal ideal, as every maximal ideal is prime. But on the other hand, if the same question, if I ask instead of 5, if I say whether the ideal generated by 7 is a maximal ideal or not, if this is a maximal ideal in Zi or not, then we can see that this 7 is congruent to 3 mod 4, which implies that this 7 is irreducible element, that we have already seen, that if some prime is congruent to 3 mod 4, then this is an irreducible element. Therefore, 7 is an irreducible element, and hence the ideal generated by 7 is a prime ideal, and since Zi is a PID, every non-zero prime ideal is maximal ideal. Therefore, I can conclude that the ideal generated by 7 is a maximal ideal of Zi. So, I have just straight away used the characterization of the irreducible elements in Zi and or concluded that whether this is an irreducible element or not. Now, I will be doing another problem. So, exercise 5. So, the next problem says that let R be the set of all functions from the real number R to real number R such that f is continuous. We have already seen that this set R forms a ring with pointwise addition and pointwise multiplication. So, this ring we would like to show that the set I, which is nothing but the collection of all the elements in this ring such that f of 0 is equal to 0. This is a maximal ideal of R. So, in order to show that this is a maximal ideal of this ring, I will try to show that if I consider the quotient, then that quotient will be a field. So, if I would try to see how the quotient look like, I will just define a map from this ring R to the set of real numbers. Say phi is the map. How I am defining this phi? So, phi of any continuous function f, I am sending it to the evaluation map that f evaluate at 0. So, this phi map how it is defined? So, as an input it takes a continuous function from R to R, and as an output it is we are just evaluating that continuous function at the point 0. Now, it is not difficult to check that phi is a surjective ring homomorphism. So, phi is a surjective ring homomorphism, and if you see what is the kernel, and kernel of phi is nothing but the collection of all the functions in R such that phi of f is equal to 0. So, this is nothing but the collection of all the functions such that f of 0 is equal to 0, and this is nothing but this ideal I. Therefore, if I use now the first isomorphism theorem, then what does it tell? So, then by first isomorphism theorem, we can write that R quotient I is isomorphic with the field of real numbers. Therefore, this R quotient I is a field. Therefore, this is a field, and hence I is a maximal ideal. So, you can see that this isomorphism theorem is very useful in order to identify the structure of the quotient ring, and in this case we have identified that this quotient ring is in fact isomorphic with the field of real numbers, and hence I is a maximal ideal in this case. Now, I will do one more example, and So, let us consider R to be this polynomial ring in two variables x and y, and I is the ideal generated by x square plus y square minus 1 by these two polynomial x plus y minus 1. Then the question is, find all the maximal ideals of the quotient ring R quotient I. So, now this is an application of Hilbert-Nullstanz's theorem. So, if you see, we have already seen that how does the maximal ideals of this quotient ring look like. It will be the maximal ideals of R which contains I. And how does the maximal ideals of R will look like? So, we know that maximal ideals of R are of the form M equal to x minus a comma y minus b for some AB in C2. Corresponding to every point in C2, I can have a maximal ideal which will be generated by two linear polynomials of the form x minus a and y minus b. And how does the maximal ideal of this quotient look like? So, the maximal ideal of R quotient I is of the form x minus a y minus b quotient I, such that this point AB is in the variety of this ideal I. So, if I consider this, now we have to find how many points are there in the variety. So, if you see what are the this ideal I is generated by two polynomials. So, if I draw the picture, then the first one is the circle, equation of a circle. So, this is x square plus y square minus 1, and the second one is the straight line x plus y minus 1 equal to 0. So, if I solve these two equations, then in the variety there are 2 points. One is the 0 1, another one is the 1 0 points. So, therefore, I can see that there will be two maximal ideals in this quotient. So, since variety of I is having just 2 points 1 0 and 0 1, therefore, the maximal ideals are x minus 1 comma y quotient I and x comma y minus 1 quotient I. So, using the Hilbert-Nullstanzas, we can easily identify what will be the maximal ideals in this quotient ring. So, with this I will stop here. I hope you have enjoyed this course. Thank you.